There exists a problem at the very edge of our understanding that astronomers have been wrestling with for decades. It's not about where the universe came from or how it will end. It's something far more immediate and unsettling. It's about a fundamental question that should have a clear answer, but somehow doesn't. What is the largest star we can possibly find? On the surface, this sounds like a straightforward empirical question. We have telescopes, we have measurements. We can look out into space and identify the biggest stellar objects. The problem is that the universe seems designed to make this answer as complicated as possible. The objects we're searching for are thousands of light years away, hidden behind veils of dust that block visible light, and their sizes shift with every new measurement technique we develop. Today, we're going to climb that cosmic ladder together, starting from the smallest sparks of starlight and ascending towards something so monumentally vast that your mind will struggle to contain it. We'll discover why bigger doesn't always mean older, why the smallest stars might outlive us by trillions of years, and what happens when a star swells so large it practically tears itself apart. But first, we need to understand what a star actually is. Let's begin where we belong, on Earth. Our planet is genuinely impressive on a human scale. It takes weeks of continuous travel to cross its surface. The distance to the moon feels vast when you actually think about it. The distances within our solar system seem almost incomprehensible. And yet, the moment you place Earth in its true context, something shifts. Our world shrinks. It becomes what it actually is, a speck, a fragment, a marble floating in an ocean of darkness. The sun dominates our neighborhood so thoroughly that it comprises 99.86% of all the mass in the entire solar system. Every planet, every moon, every asteroid and comet combined doesn't add up to even a fraction of 1%. The sun isn't just the largest object in our region of space, it's almost incomprehensibly more massive than everything orbiting it. And yet, the sun is nothing special. This is where our journey truly begins. Among the stars, our sun occupies the middle ground. It's neither remarkably large nor particularly small. It's not the hottest, not the coldest. If you were to plot every star we know of on a graph measuring temperature and brightness, the sun would sit almost dead center. This comfortable median position tells us something profound. Most stars are smaller than the sun. The vast majority, in fact, the smallest true stars are called red dwarfs, and they occupy a category that should seem paradoxical. These objects are massive enough, over 100 times Earth's mass, to sustain the nuclear fusion that defines a star, but they're so stingy with their fuel, burning it at such a glacial pace that they'll keep burning for 10 trillion years or more. That's 1,000 times the current age of the universe. Think about that for a moment. The universe itself is only about 13.8 billion years old, and there are stars that will outlive it by factors of time so absurd that the numbers lose all meaning. Red dwarfs are the universe's long-term investors, slowly accumulating interest across timescales that dwarf civilizations, galaxies, and perhaps the universe itself. As we move up the ladder in stellar mass, something interesting happens. The stars get hotter, brighter, and more massive. But here's where intuition breaks down. They don't get proportionally larger. Double the mass doesn't mean double the size. The relationship is far more violent. A star just 8 times the mass of our sun glows thousands of times brighter. It shines with a deep blue light and will burn through its fuel and explode in a supernova in mere tens of millions of years. These massive main sequence stars are rare precisely because their brief, intense lives mean we're less likely to observe them at any given time. It's a game of probability. A long-lived red dwarf will be around almost forever. A massive blue giant burns so quickly that it's almost a cosmic mayfly. We're more likely to find the slow burners than the bright flashes. At the extreme end of the main sequence sit objects like R136A1, a star that seems to mock our attempts at understanding stellar physics. With somewhere around 300 times the mass of our sun, this object burns with such ferocity that it releases as much energy in 4 seconds as our sun produces in an entire year. It's so luminous, so unstable, so massive that it's literally blowing itself apart in stellar winds that hemorrhage material at rates that seem wasteful beyond comprehension. Every second, this star loses material equivalent to the entire mass of Jupiter escaping into space. And yet, despite this extraordinary mass and power, the star is barely 40 times larger than our sun. This seems to violate everything we expect about stellar physics. A 300 solar mass object should be enormous. Instead, it's relatively compact, held together by gravity so intense it can barely contain the nuclear inferno at its core. This brings us to one of the most counterintuitive discoveries in stellar astronomy. Size and mass are not the same thing. Mass and brightness correlate beautifully on the main sequence. The heavier a star is, the brighter it burns. But size is governed by entirely different physics. The smallest objects can be the most massive, the largest objects can be relatively lightweight. This disconnect becomes the key to understanding the stellar giants we're pursuing. Every star eventually runs out of fuel. Our sun has been burning hydrogen in its core for about 4.5 billion years. Now, it will continue for another 5 or 6 billion before the hydrogen finally exhausts itself. When that moment comes, something dramatic happens. The core contracts suddenly, gravity pulling inward with tremendous force. But that gravity doesn't win outright. The compression heats the core to temperatures so high that a new fusion reaction ignites. Helium begins fusing into heavier elements, and this release of energy pushes back against gravity with such force that the outer layers of the star expand, not gradually, explosively. The sun will swell until its surface reaches approximately where Mercury orbits today. It will consume Mercury entirely. Venus will be engulfed. Earth will be bathed in temperatures so extreme that our oceans will evaporate in seconds. The sun will become a red giant, and it will remain that way for a brief moment in cosmic terms, a few 100 million years, before it collapses into a white dwarf and slowly cools for the rest of eternity. This transformation happens to all stars that live long enough to exhaust their hydrogen. The precise size they reach depends on their mass. A star just slightly more massive than the sun might swell to dozens of times its original radius. Certain red giants we observe today have radiated hundreds of times that of our sun. Consider a star named Mira, which is part of a binary system only about 42 light years from Earth. Mira has only about 1.5 times the mass of our sun. It's not a particularly massive object, yet it has swollen to approximately 330 times the sun's radius. Imagine that. 1.5 times the mass, yet occupying a volume so enormous that the sun could fit inside it thousands of times over. The density of Mira's outer layers is so thin that scientists often debate whether you could even call it a solid surface. It's more like the star gradually fades from extremely tenuous gas into the vacuum of space. But red giants are just the opening act. When we move to stars that begin their lives with 8 or more times the mass of our sun, the rules change. These objects don't simply become red giants, they become red supergiants, and this distinction matters enormously. The mass threshold is crucial because it determines not just the size these stars can reach, but the complexity of their evolution. These massive stars don't fuse hydrogen for billions of years like the sun. They burn through it in millions of years, sometimes only hundreds of thousands. When the hydrogen exhausts, the helium fusing phase begins, but again they burn through it rapidly. Then carbon fusion, then neon, then oxygen, then silicon. Each new stage produces less energy and consumes fuel faster than the last. The core of a dying red supergiant resembles an onion with layers of different elements fusing at different rates. Hydrogen burning in the outermost shell, helium underneath, carbon, neon, oxygen, iron in the center. Silicon fusion lasts only about a day before the core becomes so dense, so hot, that it collapses catastrophically and ignites iron fusion. Iron fusion is different. It doesn't produce energy. It consumes energy. When iron atoms fuse, the process pulls energy out of the core rather than releasing it. And when that happens, there's no force left to hold the star up against its own crushing weight. The core collapses in less than a second, compressing to roughly the size of Earth, but containing more mass than the Sun. And then it rebounds. The shock wave tears through the star at tremendous speeds, initiating a supernova explosion so powerful it can briefly outshine an entire galaxy of billions of normal stars. But we're getting ahead of ourselves. Before that cataclysmic final moment, these massive stars spend their final millions of years as red supergiants. And it's during this phase that they reach sizes that challenge our ability to visualize. Betelgeuse is perhaps the most famous red supergiant in the night sky. It's the red shoulder of the Orion constellation, and it's been known since ancient times. If placed where our sun sits, Betelgeuse would extend almost to Jupiter's orbit. It would contain the entire inner solar system within itself. Antares, located in the constellation Scorpius, is similarly enormous. These aren't hypotheticals, these are real objects we observe regularly. Yet, even these impressive supergiants are not the largest stars we know. The search for the biggest star leads us deeper into the galaxy and farther from the familiar. There exists a region of space in the constellation Scuti where astronomers discovered something that seemed almost impossible when the data first came in. A star so large that it defied the models they'd constructed to understand stellar evolution. They named it Stevenson 218, honoring the astronomer who identified it in infrared surveys. The designation doesn't convey the strangeness of what this object actually is. Stevenson 218 has a radius of approximately 2100 times that of our Sun. Not thousands, not hundreds, over 2000 times larger. To process that number, let's use some comparisons. If the Sun were the size of a basketball, Stevenson 218 would tower over a 20-story building. If you traveled in a spacecraft at the speed of light, the fastest anything can possibly move, it would take you more than 8 hours to circle this star once. 8 hours going as fast as physics allows. The volume is even more staggering. You could fit approximately 10 billion suns inside Stevenson 218. 10 billion. If every sun in our Milky Way galaxy, all 100 to 400 billion of them, suddenly appeared inside this single star, there would still be room left over. The surface area of this object is so enormous that it radiates light with the power of hundreds of thousands of suns, and yet the star is relatively cool, only about 3200 Kelvin. That's roughly 60% the temperature of our sun's surface. This contradiction sits at the heart of understanding these stellar giants. The Stefan-Boltzmann law of physics tells us that the total energy radiated by an object depends on both its temperature and its surface area. A star can be dim but cool or bright but cool depending on its size. Stevenson 218 compensates for its relatively low temperature with an absolutely enormous surface. Every square meter of the star's surface radiates energy according to the Stefan-Boltzmann law. When you have a surface area so vast that it's almost incomprehensible, even that cooler radiation adds up to an extraordinary total luminosity. The star is shedding mass at an alarming rate. Every year, it loses material equivalent to about 1/10,000th of the sun's entire mass. Every 3 years, it loses material equal to the entire mass of Earth. This material forms a thick envelope of gas and dust around the star. The envelope is so dense that visible light can barely penetrate it. Infrared radiation with its longer wavelengths passes through far more easily. This is how astronomers discovered the star in the first place. It showed up as an anomalous infrared source in their data. Stevenson 218 didn't achieve its current size naturally. Or rather, not entirely naturally. The star probably began its life with a mass somewhere between 20 and 40 times that of our Sun. It wasn't the most massive star possible, but it was well above average. As it evolved, it swelled into its red supergiant phase and grew to enormous proportions. The fusion in its core progressed through all those stages we discussed, consuming hydrogen, then helium, then carbon, then everything else. The star's current size suggests it's in an extremely advanced phase of evolution. It's probably lost roughly half its original mass in the process. All that missing material is now scattered in shells of gas and dust, extending far into space. Most remarkably, the star will likely continue losing mass. Some of these red hypergiants periodically shed enormous quantities of material in violent eruptions. A single outburst can launch an amount of gas equivalent to several times Earth's entire mass into space at speeds of hundreds of kilometers per second. These aren't gentle stellar winds, they're explosions. The discovery of Stevenson 218 didn't settle the question of which star is largest. It complicated it further. Before this star's prominence in the astronomical literature, UY Scuti held the record. Discovered back in 1860 by German astronomers, UY Scuti was measured to have a radius of approximately 1,700 times that of the Sun. It would still be enormous, still almost impossibly large. But when the European Space Agency's Gaia spacecraft released its precision distance measurements, astronomers rushed to recalculate the distance to UY Scuti. The new parallax measurements showed that the star was significantly closer than previously thought. Closer distance means smaller apparent size. The revised radius dropped to roughly 99 times the Sun's radius, from one of the largest known stars to barely more impressive than some other supergiants. The implications were staggering. If our distance measurements were this far off for a famous star we'd studied for over a century, how many other measurements were similarly flawed? This is where stellar astronomy gets messy. The stars we're trying to measure are thousands of light years away, surrounded by dust and gas that obscure them, pulsating with variable brightness, and perpetually shedding material that makes it difficult to determine where the star ends and the surrounding nebula begins. Different measurement techniques, infrared observation, optical spectroscopy, radio observations of masers, theoretical models based on luminosity and effective temperature, produce different results. The error margins can be enormous. 50% uncertainty isn't uncommon. Sometimes larger. This means that the title of largest known star genuinely changes as new observations come in and old measurements get revised. It's not a fixed fact, it's a moving target. Several contenders vie for the crown. NML Cygni, a star shrouded in dust in the constellation Cygnus, has radius estimates ranging from approximately 1,200 to nearly 3,000 solar radii, depending on which measurement technique and distance estimate you use. Vi Canis Majoris, perhaps the most famous red hypergiant after UY Scuti, has appeared in scientific literature with sizes ranging from 1,400 to nearly 2,000 times the Sun. WOHG 64, located in the Large Magellanic Cloud outside our galaxy, presents its own challenges due to its extreme distance. We can barely resolve it as anything more than a point of light. Some recent studies suggest it might be entering a yellow hypergiant phase, undergoing a dramatic transformation. But we can't be certain. What becomes clear when examining all this data is that Stevenson 218's title as largest known star comes with enormous caveats. The measurement uncertainties are large enough that several other candidates could potentially exceed it. But among all the contenders, Stevenson 218 has been studied in the most detail and remains the best supported claim. It represents our best current answer to a question that might seem simple but is devilishly complex in practice. The physics behind these giant stars reveals something surprising about the universe. Stars don't naturally grow larger as they accumulate more mass. The opposite is usually true. More massive stars are denser, more compact, shining with ferocious intensity from relatively small surfaces. It's only as they die, only as they exhaust their fuel and undergo dramatic transformations, that they swell to these cosmic proportions. There's a theoretical limit to how large a star can grow. It's called the Hayashi limit, named after the Japanese astrophysicist who derived it. The limit relates a star's mass, temperature, and radius in a mathematical relationship that defines an upper boundary on a graph. See, if a star's properties place it beyond that boundary, it becomes unstable. The star can't maintain equilibrium. Convection in the outer layers becomes chaotic. Radiation pressure overpowers gravitational binding. The star begins shedding mass in violent eruptions. It contracts slightly, heating the surface and increasing its luminosity. It's a feedback loop. The largest stars we observe are hugging right up against this theoretical limit, balanced on a knife's edge between stability and catastrophic mass loss. This raises a profound question. Are Stevenson 218 and stars like it the absolute largest that physics permits? Or are they merely the largest we've found so far, with undiscovered titans lurking in undiscovered regions? Astronomers have systematic blind spots. Much of the galaxy is obscured by dust. Distant regions of space contain stars we simply haven't observed. The infrared surveys that revealed Stevenson 2-18 are ongoing, and they continue uncovering red supergiants hidden in dusty stellar nurseries. The James Webb Space Telescope, with its unprecedented infrared sensitivity, might reveal even larger objects. Or it might confirm that we've found something close to the actual maximum. The future evolution of Stevenson 218 is simultaneously mundane and spectacular. The star will continue its current phase for perhaps a few million years. During that time, it will almost certainly lose even more mass. Some red hypergiants periodically transform into yellow hypergiants, a state characterized by even greater brightness and a slightly higher temperature. This yellow hypergiant phase is brief and violent. The star sheds its outer layers, shrinking and heating as it does. Only about 15 yellow hypergiants are known to exist, suggesting they're an extremely short-lived intermediate state. Stevenson 218 might undergo this transformation, or it might skip directly into what comes next. Eventually, probably within the next few million years, Stevenson 218 will exhaust all possible fusion reactions in its core. The ion barrier will be reached, the core will collapse in milliseconds, and a supernova explosion will tear the star apart. If the star retains enough mass at that point, the explosion might forge a black hole. If it's shed enough material through stellar winds, the explosion might create a neutron star instead. Either way, the result will be a cataclysm that, for a few weeks, outshines the combined light of millions of galaxies. Then, as quickly as it began, the light will fade. The expanding remnants will cool and dim, and the material of which Stevenson 218 consists will scatter throughout space. This is the most profound point in this entire story. The iron in your blood was forged inside massive stars. The oxygen you're breathing was created in stellar furnaces. The calcium in your bones, the carbon that forms the backbone of every organic molecule in your body, all of it was manufactured inside stars through nuclear fusion. And then, when those stars died, when they exploded in supernovae or shed their outer layers in stellar winds, they scattered that material into space. That material eventually coalesced into nebulae. Those nebulae became new stellar nurseries. New stars formed, planets accreted around those stars. On at least one of those planets, simple chemistry became complex chemistry, became life. You exist because stars like Stevenson 218 died and scattered their elemental legacy across the universe. The quest to find the largest star isn't just about establishing a record, it's about understanding the boundaries of physical law. What determines the maximum size? Is there a physical ceiling? Could we be missing an entire class of even larger stellar objects? Could stars grow larger still? These questions remain tantalizingly open. The Hayashi limit suggests there is an actual boundary, but limits can sometimes be exceeded through processes we don't fully understand. 20 years ago, astronomers would have said that stars like Stevenson 2-18 shouldn't exist. The prediction said the universe couldn't manufacture objects that massive that burned that bright, yet here it is. The reality exceeded theoretical expectations. As we stand at the edge of our current knowledge, peering into dusty regions of space and waiting for new telescopes to come online, we can't help but wonder what other surprises await us. The universe has repeatedly shown a willingness to be stranger, more extreme, and more wonderful than we anticipated. Stevenson 218 might be the largest star we ever find, or it might be merely the largest star we've found so far. Either way, the pursuit of understanding these stellar giants teaches us something fundamental about the cosmos. It teaches us that scale is relative, that the universe operates on dimensions our brains simply cannot intuitively grasp, and that somewhere in the darkness between distant suns, structures exist so vast and so magnificent that they humble everything we thought we knew. The largest stars in the universe might be distant and cold and difficult to observe, but they're real, they're there, and they're waiting for us to understand them.